Hello everyone and welcome back. So we've made it to chapter 14 now, and now we're going to talk about something important. The work of a force and the principle of work and energy. So after today, hopefully we'll figure out how to do the work of a force and understand how to use work and energy to solve problems. So let's jump into the applications. First off, a lot of you have probably been on a roller coaster before. It lifts you very high into the air, and then it uses gravitational force to assist the car in reading high speeds in the valleys of the track, and even allowing them to go over loop-de-loops. Now, how could you design the track to control the forces experienced by the passengers? Because quite obviously, if this is too sharp, it will actually kill them. And we don't want that. Too sharp curves that kill our passengers, not a good idea. And also, if it's too high, well, it's going to be dangerous because they'll get to too high velocities. So we've got to make sure that it's a safe ride. But how are we going to do that? Or in this case, you might see on the highway there's these crash barrels, which are actually filled with a lot of water or some other liquid to absorb a car's kinetic energy in a nice elastic way before it hits this barrier right here. Because you don't want to hit that barrier. Now, if you knew the velocity of the car that was coming in, and you also knew the amount of energy that one of these barrels could absorb, how many would you need to cushion that car? Do you think we can figure that out? Well, the answer to both these questions is yes, we can, and we're going to use the principles of work and energy to help solve them. So, where do we get the work and energy equations? Well, they're derived by integrating the equation motion with respect to displacement. So we're going to substitute in that our acceleration is equal to our velocity times the change in velocity with the change in path. We know that. And when we integrate this, it is going to yield an equation that is known as the principle of work and energy. Now, this principle is very, very useful for solving problems that involve force, velocity, and displacement. It can also be used to help us explore the concept of power, which is just simply energy over time. Now, if we're going to do this, though, we have to first understand how to calculate the work of a force. We'll come back to this, though. Don't worry, we're going to come back to this. We'll do some examples to help show what we mean by this. Now, a force does work on a particle when the particle undergoes a displacement on the line of action of the force. A force does a work on the particle when the particle undergoes a displacement along the line of action of the force. Now, what do I mean? Well, for example, if I pick up a box, I'm lifting it up, I'm holding it with my hands now, terrible hands, and I move forward. Okay? I move forward. I'm having to work on that box to move it forward. There is some frictional force because the box is going to resist me, and eventually I'm going to get it to where it needs to go. Or if I am pressing on a box and it's on the ground, I'm having to apply some force and it's going a certain distance. And the distance plus the force it took me to do that is going to be equal to the work I did. Now, to make this a bit more general, because in real life, our forces and our displacement are not always in the same line. We need to say that, okay, well, the work, incremental work of this force is going to be equal to the incremental distance I traveled times cosine theta. So this is the angle in between the force and my displacement vector. The force and my displacement vector. And of course, if we integrate this, we can get the total work done by integrating from where I began to where I ended. Now, one common case we'll run into is that force will be a function of position. Now, if that's the case, we can get something like the following. Now, if both the force and the angle are constant, then this equation will further simplify. We can see my energy is going to be, my work is going to be equal to my force times the angle between the force and my displacement times my displacement. Now, work is positive if the force and the movement are in the same direction. However, if they are opposing, then the work is negative because you are removing its energy. If the force and displacement directions are perpendicular, the work is 0 because we have cosine of theta here, and when theta is 90 degrees, it goes to 0. So, I hope this helped you. Thank you for listening, and I'll see you all next time. Bye-bye.